Okay, here's the thing. Science is amazing. We've landed robots on Mars, cured a multitude of diseases, and even created jelly beans that taste like dirty gym socks. But sometimes, science isn't just a knowledge creation engine, it can become a worldview, a lens through which we not only view the mechanistic function of our world, but also morality and purpose. When it's used outside of its functional scope, science can lead us astray. Here are 10 mistakes that science can make when we're not careful in its application. Number 1. Assuming that if something is untestable, it must be false, or at least unimportant. This can create the biased perception that some concepts, like philosophy, morality, aesthetic beauty, or anything else inherently subjective, well, these are not worth thinking about. Even objective concepts that are beyond our technological capacity for modern scientific study may similarly be dismissed as irrelevant. This can also look like applying science to non-scientific problems, using scientific principles and empirical data in an attempt to define things like meaning, value, ambitions, perspectives, or morality. Number 2, conflating lack of mechanism with lack of effect. In other words, mistaking absence of evidence for evidence of absence. An effect can be observed and true even if the mechanism of action is unknown or unintuitive. And prematurely dismissing a predictable phenomena simply due to a lack of understanding of the mechanism can be harmful to the scientific process. Now, to be fair, if a scientist doesn't know why something might be happening, it can be hard to design a good test to verify it. That said, clever and open-minded scientists will still find ways to parse reproducible outcomes, even from observational studies lacking a proposed mechanism of action. Number 3, the naturalistic fallacy, or assuming that if something is, then it also should be, or is good. For example, assuming a trait that is evolutionarily adaptive must also be socially, culturally, or morally preferable. In other words, assigning some judgment or value claim to something solely because it's empirically or scientifically observable or reproducible. Number 4, overconfidence in consensus as final truth. Or in other words, over-reliance on replicated experiments as an indicator of truth. Now, while experimental reproducibility is vital for the accuracy of scientific claims, it can also occur due to biases in experiment design, or artifacts or limitations of testing, or incorrect interpretations of results. We've seen examples of this historically, such as scientific resistance to the idea of continental drift until the 1950s, or resistance to the idea that stomach ulcers were caused by bacteria rather than stress or our diet. Or nutritional claims, like that foods high in cholesterol cause high blood cholesterol, or that foods high in fat cause obesity. All of these are examples of claims that were once supported by consensus and popular opinion among scientists, but were later found to be false. Number 5, overvaluing quantitative data relative to qualitative data and anecdotes. Or in other words, assuming that because some observation lacks quantitative metrics, it must be false, or unimportant. Now, it's true that anecdotes are not data, but qualitative information is still useful for informing hypotheses and experiment design. Number 6, failing to notice bias or lack of neutrality even in well-designed studies. For example, choosing what to study and what not to study can itself be a form of bias. Topics of study often reflect funding priorities or institutional incentives or cultural assumptions, not necessarily objective importance. Within peer-reviewed scientific literature, there can be a publication bias towards studies with statistical significance and against negative or fail to confirm studies. And even when methodology is solid, how the results are framed can reflect implicit bias in order to please the funders or the journals or tenure committees or just popular public sentiment, especially on contentious issues like social justice, the economy, and the environment. Number 7, assuming that scientific truth overrides impact. In other words, pushing scientific facts because they're demonstrably true, regardless of the impact that those truths have on their intended audience. For example, science may accurately correlate health conditions to metrics like BMI, age, or race. But unless it's very clearly worded, people may interpret these results as a diagnosis or a stigma. That is, for example, people may overfocus on the metric, such as BMI, rather than the condition it's correlated with, such as metabolic disease. Or, for example, in climate science, even if climate models are accurate, it's still a question of if, how, and to what degree we should address climate concerns, as this is a multifaceted problem which cannot be decided solely by the climate consequences that climate scientists predict. Number 8. Overfitting complex mathematical and statistical models to messy data. Now, this can also be called data dredging or p-hacking, and it can make an effect seem true even when it isn't or when it's negligible or irrelevant. Data dredging can be silently encouraged by academic institutions which provide prestige and job security to professors who publish, and publishing is more likely when studies show some sort of predictive model or statistical significance. Speaking of which, number 9, confounding statistical significance with impact of effect. A statistically significant effect does not imply practical significance. Again, this error might be reinforced by scientific institutions which might prioritize and reward studies by publishing those that demonstrate statistical significance, even if the real-world impact is minimal. And number 10, treating the scientific model as the reality. The map is not the terrain. This could look like using population trends to evaluate individuals, or deciding whether an individual weather event was caused or not caused by climate change, or using a model to make predictions outside of its defining bounds, also known as extrapolation. As they say, when you're a hammer, all you see is nails. Scientists may struggle to observe phenomena from perspectives outside of their own intellectual domain of expertise. So those are 10 areas where scientists may make mistakes. Thanks for listening. Next time we'll talk about the 10 things that we can get wrong when we avoid or misunderstand science.